So let's do an example using the BiotSavart law. Now this example is, it's going to get a little bit crazy, but it's not too bad. And actually, just follow along with the steps. What we're really going to do is use the results of this example. So the results are the most important thing. Okay. Suppose I've got a wire like this. So this is here's what we're given. We've got a wire, and up here is our point in space, and here's our current flowing through this little line segment, and we're just going to look at this one part of the line segment. And what I'm going to do to make this solvable, barely, is I'm going to call, this is going to be my origin right here, and this is going to be my x-axis. And I'm going to say, okay, and I'm going to call this, here's x from here to here, and I'm going to go from here all the way over to there. And I'm going to say, okay, what's the magnetic field right there? So I want to find B at point P. Okay, and I need to identify a few other values. We're going to call this distance A. So A is the distance, the shortest distance to the wire. It's the perpendicular distance, right? Like this. Now, so what I'm going to do is I'm going to use the BiotSavart law to figure out what this is, what the magnetic field is right there. And so that says that B is equal to, okay, think constant of proportionality. Mu naught I, or mu naught over 4 pi, and then times I, and then we have the integral. Okay, what does it depend on? Well, it depends on I, but I is a constant, so it came out of the integral. It also depends on how long this wire is, which I'm going to represent with ds, over r squared. Now, to get the direction of this, though, you need to cross it with r hat. Now, that's how I reconstruct the BiotSavart law. I just look at, okay, what does it depend on? And I think about it, and now it kind of makes sense to me. And it may for you after you've taught this for 15 years or so. Okay. And by then, life is basically over. All right. So I want to evaluate this integral, but I've got to look how many variables I've got. I've got ds, which I can call dx. Here's my let's put a little we'll put a little dx right here. There's my dx is right there, and we'll put it in the I hat direction. And so now I've got to start working on this. Mu naught I over 4 pi times this integral, and I have a dx, whoops, in the I hat direction, crossed with r hat, and I'm going to be able to get rid of that in just a minute, over r squared. Okay. And, well, let's take a look at this right here. Here's r hat. The first thing you need to do is really identify where r hat is.
Can you zoom in a little bit?
Okay. And here's theta. Oh, and theta is, remember, the angle between dx and r hat. So we can right away tell that this is going to come out of the board right here. The direction of this is going to be out of the board. And if I say, okay, this is I hat, j hat, and then k hat is coming out of the board, then we can see that the magnetic field is going to be, at that point, is going to be in the k-hat direction. But before we get to that, let's travel from here over to here. So we've got, when you're over here, look at the angle has changed. Here's, we'll call this theta 1, or my initial angle, and this over here is theta 2. So we're going to go from this angle over to this angle. Okay? Well, this cross product right here, remember the cross product is, let's see, B is equal to mu naught I over 4 pi times the integral. Well, we've got a dx. Now, a cross product is this times the magnitude of this times the magnitude of this times the sine of the angle between them over r squared. And we know that I hat cross r hat, in this case, for everywhere, wherever r hat's going to be, it's going to be out of the board. So we're going to say that that's in the k hat direction. Okay? But look, I've got 3 variables in here. I've got dx, I've got theta, and I've got r. If I'm going to integrate this, what do I need to do? I need to get all of them in terms of the same variable. Now, most of you are in AP Calc right now, either A, B, or BC, and you need to learn how to do that. So what we're going to do is we're going to get r. We're going to get, one way of doing this is to get x in terms of theta, or dx in terms of theta, and r in terms of theta. That turns out that's the way we're going to do this. So now let's look at this picture. We have x and a and r, and we have theta right here. So let's get what is x going to be equal to in terms of r and theta? So x is equal to r cosine theta. Does that make sense? And is that right? Hold on. Oh, I wonder if this will work. I need to hold, because I'm doing it differently than the book did, but I think that this is correct. You know what? I'm going to stick with, hold on. I'm not going to do that. I'm going to say that, let's go r for a second. R is equal to a over sine theta. Do you all agree with that? A sine theta, r equals a over sine theta. And then I'm going to do this. I'm going to say that x is equal to negative a, and I have to start moving fast, so I'm going to just cotangent of theta. Now, how do we get that? Well, let's actually derive this. Hopefully I'll get this done in time. The tangent of theta is equal to a over, but look, x, this is my origin right here, so we have a negative x over here. So x is equal to a over negative tangent theta, and so x is equal to negative a cotangent theta. And actually, you know what? I don't think we could have used this. Well, we'll just stick with that. That's what the book did. All right. Now, we don't want to replace x, though, do we? We want to replace dx. So take the differential of this. You get dx is equal to, and I'm just going to copy it down, cosecant squared theta d theta. Now, if you don't believe me, just look up the derivative of cotangent. You get negative cosecant squared theta. Okay? So just look it up. Just believe this. Okay? Now, if I replace r with this and dx with this, I get b is equal to mu naught I over 4 pi. Now, this is, by the way, this is going to be worth doing. Okay? And this is going to be, well, dx is a cosecant squared theta. There's d theta. I want d theta. And then we have sine theta still over here. Over, and then what is r squared? It's, isn't this a cosecant theta, right? R, if r equals a over sine theta, then r equals a cosecant theta, right? 1 over sine theta is cosecant. Well, we're squaring it. So we get a squared cosecant squared theta. And that is our, now did I leave anything out here? I left out the k hat direction. Okay. Now, this is very complicated and messy, but look what happens. Woohoo! Okay. And this cancels that. So we get an a that comes out now. And we have, put an a right there, times the integral of sine theta d theta, which we know how to do that, right? And then we're going to go from theta 1 to theta 2. Okay? So what is the integral of sine theta d theta? So this is equal to negative mu naught I over 4 pi a times cosine theta 2 minus cosine, am I still on camera? Barely. Cosine theta 1. At least I'm paying attention now. Now we can get rid of this negative by just switching the order of these two. And this is my answer. The strength of the and we keep leaving off that k hat direction. K hat. So B is equal to mu naught I over 4 pi a times cosine theta 2 minus cosine theta 1. Sorry. Just seeing if you're paying attention. Cosine 1 over 2. Voila! Woo! Okay. Oh, k hat, thanks. Thank you. Okay. So, now that is what we were trying to do. And we did it. So if you know the angles, we can now figure out what the strength of this magnetic field is. That's awesome. But that's not the end of it. Okay? Watch this. And this is a beautiful thing. What if this is a really long wire? Okay, let's go back to our wire. Let me zoom all the way out so you can see everything. Okay? Now, by the way, if this is just a bunch of fancy derivation stuff to get to this. What if this was a really long wire? Woo! Really long wire. Off the table. Okay, now, if the wire is super, super long, So if the wire goes to infinity and beyond, what happens to theta 1? What does theta 1 go to? Look at the picture and think. Here's theta 1 right here. There, if I say, oh, we're going to make this super long, what is theta 1 going to as I go infinitely far away? Think. What does it go to? What angle? It goes to 0, right? Look, if this picture right here, if this wire was 4 miles long, and you were to try to measure what theta 1 is, it's going to be practically 0. So we're going to say it goes to 0. And what about theta 2? What does theta 2 go to if the wire goes to infinity? It goes to 180, or pi. Let's just use pi. Okay, so if I say, well, B is equal to mu naught I over 4 pi A times, now we're going to say if you let the wire go to infinitely long, then you have cosine of 0 degrees, or 0 radians, minus the cosine of pi. Well, what is the cosine of 0? It's 1. Minus, what's the cosine of pi? Negative 1. So what's 1 minus negative 1? 2. So we get a very important result. That's why I'm spending so much time on this one example. A very, very important result that we're going to use over and over again, and you need to memorize this equation. This is 2. Cancels with the 4. Mu naught I over 2 pi A. If you have a really, really, really long wire and you want to measure the magnetic field, this is the equation you're going to use. So this is the magnetic field for a long wire. Now, let's think about this one more time. When can you use this equation? Okay, well, what defines what a super long wire is? When the length of the wire is much, much, much greater than what? A. If the length of the wire is much, 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 much greater than A, you can use this. So it doesn't have to be infinitely long. It just has to be really, really long compared to A. So if you have a really short wire, say my wire length was only that long, when can I use this equation right here? When A is right here. Now, if A becomes big compared to the length of the wire, then you have to use this guy right here. Okay? Which is okay. It's not so bad. All right? Now, we are going to use this result a lot. Okay? So that is the first example we're going to do.